Hello and welcome to Network Collective. Today we're going to talk about what your mama never told you about OSPF. Check your headphones, get comfortable, and get ready for a deep dive into OSPF. Joining us again for our discussion of OSPF, we have Nick Russo and Russ White. Nick, why don't you introduce yourself and tell us where we can find you?
Hi, everyone. My name is Nick Russo. I'm a network engineer at Cisco. I support a U.S. federal government. You can find me on Twitter at NICKRUSSO, Nick Russo, with the numbers 42518 after it. And you can also search for me on LinkedIn.
All right, great. And Russ?
Russ White, LinkedIn, network architect, whatever, routing geek. You can find me at roll11.tech is kind of a central place to find me, but you'll also find me on Packet Pushers, Network Collective, and LinkedIn, among other places.
All right. Today we are going to do a deep dive into OSPF. So let's start off by discussing what OSPF does well.
What OSPF does well? Well, that's a null set.
Oh, no. So quickly.
So quickly.
So, let's get it out of the way. Russ, what's better than OSPF?
Anything? No.
Not static routes. Come on.
No, not static routes. You're right. And not RIP. Okay, fine.
All right.
So what does OSPF do well? OSPF does full meshes really well. It does kind of partial meshes very well. It does rings pretty well if you know what you're doing. You got to be really careful with microloops, which I'm sure we'll talk about. But anything that's kind of triangle based is really good for OSPF. And actually, it does really well at scale. There's kind of a myth about link state and scale that you can't do a large number of routers with a link state protocol. And that's really just so old school and so yesterday. You can do so many routers nowadays with a link state protocol. So that's pretty much just about everything is pretty much within OSPF's purview as far as working well on topologies, except just a couple. There's a couple that it doesn't do well on.
To say there's very clear, one that's missing in there, and that seems to be hub and spoke. So why did
hub and spoke.
Why did you not include hub and spoke in things that OSPF does well?
Well, OSPF, like most link state protocols, is designed to have a synchronized database. And if you know much about synchronizing databases and CAP theorem, what you end up with is this big mess of trying to get, particularly in very large scale hub and spokes, to get all of your databases to be synchronized. Now, there are ways around that, of course, which I think Nick has some thoughts on that. But, there were things we used to do in TAC around, running stub type things and throwing extra hardware layers into it and doing type 3 filters and stuff like this to make it go away. But by and large, the way you solve the hub and spoke problem in OSPF is to just not synchronize the database, because the synchronization of the database is where things get really sticky. The other thing that's kind of nasty in OSPF is truly large rings. If you get a ring of 5 or 10 or 15 or 20, like in a metro area network, routers with dual connected between them, you tend to have a lot of problems with microloops in OSPF, like you do with any other link state protocol. That's just the nature of link state. So that's just kind of the way it works.
Now, Nick, you've been pretty quiet. So what are we, Russ talked about some things that OSPF does well. You can add to that, or you can pile on with the things it doesn't do well.
Yeah, so I think what Russ said is, one of the ways to make OSPF work better in a hub spoke network, or for any other network where OSPF is not performing well, would be to stop synchronizing the databases. And for those who are not aware of what the CAP theorem is, it was kind of a theorem originally developed for databases and things like that. And I think Russ has done a pretty good job of kind of adapting that and putting it into network terms. And I know you can read about that and some of the things he's published. But what it's effectively saying is you really can't. Let me just back up. So when we talk about it, we talk about in OSPF. Let me just completely back up for a second before I stutter too much. What we're really trying to say, is if we break up the flooding domains using kind of traditional OSPF tools like areas, hiding topology information through summarization, as Russ calls it, or prefix aggregation, which is kind of a second stage onto that, we can help scale OSPF that way. And I think that's kind of well known. And I don't want to talk too much about that today because I feel like that would be things that people can generally read. What I would like to share, though, is kind of being pigeonholed and being stuck in a situation where you're deploying OSPF in the hub-spoke network and you really don't have a different choice because you have to. That's what the network looks like, and you're being forced to use OSPF either from external, maybe political influences, or for whatever other reason. So something that I thought, and that's a design I'd like to share with everyone that I think is kind of valuable, and especially within the context of availability, which I'll kind of talk about in a little while. But if you think about an OSPF network and hub-spoke, no matter what you do behind the hub, and no matter what you do behind the spokes, everyone in that big hub-spoke kind of network is generally still going to have state for everyone else, especially if it's using a technology like Cisco's DMVPN or any other kind of NVMe style technology where you have a single interface at the hub and all these other spokes in the same IP subnet. You're going to have a really hard time not putting all those guys in the same OSPF area. There's some things you can do, but in general, that's a difficult problem to solve without breaking out different areas for all the other individual sites. So something I'd like to suggest, and I actually read this from Russ's book, Optimal Routing Design, a few years back, was there's no rule that says in a hub-spoke network
are still
that
reading that.
Yeah, so believe it or not, 12 years later.
You have one reader.
Still relevant, highly. But really what it comes down to is the spokes don't necessarily need state for all the other spokes, especially in a hub-spoke network. So what you can do basically is go on the hub. There's that one mysterious command for people who've worked with Cisco devices. It's that OSPF database filter all out or something like that. It's like, why would you ever use that? This is a case where you might use that. Because if the hub doesn't send state, any LSAs at all to any other downstream spokes, it can still learn information from the spokes, so it can route downstream. But how do the spokes route upstream? The answer can be a simple static route. Especially if you have a couple data center subnets that aggregate nicely, put a couple static routes on all the spokes, they can reach the DC subnets over the WAN. And the hub learns all the downstream routes, all the remote sites from OSPF. So looking at the routing tables, on the spokes, you have a static route upstream. On the hub, you have OSPF routes downstream. I would consider that an OSPF design, even though half the time you're using static routes in that case. But it works really well, and it scales pretty nicely. Spokes don't have state for other spokes, and OSPF flooding never occurs in the downstream direction. So it actually works quite well. And it's a design that I've deployed many times in production environments. And I feel like it's a good way where if you're kind of stuck using OSPF in a hub-spoke design, you'd want to look at doing something kind of like that.
So, Nick, it's really interesting to me. I know we've talked in the past about OSPF and where you're deploying it. I think you're probably one of the very few people I know who've actually deployed the mobile ad-hoc network extensions for OSPF, which deals a lot with scalability and how it works in a very fluid environment. So do you have any thoughts on that? Because that's just something that's really interesting to me because I was helping design those extensions a long time ago. It was a very specific military case, but I think you're actually deploying them, right? Is that correct in your network?
Yeah, that's true. So the case I just described was a different part of the network, a different use case, an entirely different effort than the places where we're using the MAN-A extensions or the radio aware routing. It has a couple different names, but effectively this is specific to OSPF v3. So OSPF v3 was extended effectively to support kind of mobility type stuff. So you can have a bunch of different radios, in the military application might be individual foot soldiers or trucks driving around on a battlefield, and they build kind of this mesh network. And there's been a lot of kind of proprietary protocols that vendors have designed to do their own internal routing. Of course, the whole file layer is going to be kind of proprietary. The OSPF v3 doesn't control what the radio RF layers will look like, of course. But from a routing perspective, you can use OSPF for that, as well as some extensions for OSPF v3 to have that work. And there's a whole bunch of knobs. I mean, the thing about it that kind of threw me back is just the sheer number of knobs that come with this thing, tuning things like timers, and how bad does a link have to get, and how much do I change the cost? And there's a lot of different things you can tune to try to get that network the way you want. But the thing that's really interesting about it, of course, the idea is as two vehicles move farther apart or obstructions come in between them, that link is going to degrade, and you may want to take an alternate path in a dynamic way. So I would be hesitant to give it a cool name like something like SDN, because that wouldn't be right. But what it is meant to be is more dynamic network around the quality of the links based on kind of the file layer reporting up the stack to say, hey, this link is really bad, you should go another way. The link's not down, it's up. But we want to dynamically change things like cost to go around that.
Yeah, and there are also some flooding extensions in there, flooding optimizations and neighbor optimizations that are really cool. I only brought that up because as you were talking about your other situation, I knew that was in the same network, not the same area. But it occurred to me that a lot of people don't realize just how flexible the routing protocols that we have today actually are. How much stuff you can do with them. Again, going back to the beginning of what does it do well, what does it not do well, you think about OSPF and ISIS and BGP and stuff, and you start thinking about very specific situations. You don't really think through that these protocols have been extended and they're really usable in a lot of different spaces. So it's fairly interesting. The mobile ad hoc networking extension is one that's fairly specific. It's not used in a lot of places. But it's really cool that it's actually out there and it's actually deployed and deployable. So it's just one of those cool things that kind of extends the range of what OSPF can do.
Now, you guys have brought up a couple of things here, and I kind of want to go back to them. So one of the things you brought up was CAP theorem. And then also, we're talking about distributed databases, which seems like a wholly different problem, right, than a routing protocol on the surface, but underneath, right? It's one of the critical things about OSPF. So I know, Russ, you've done a lot of content in and around both the CAP theorem as well as how networks are graphs and some of the graph theory and all that. So maybe you could summarize that. Can you do that in 30 seconds? No.
In 30 seconds, yeah. Oh no, one sentence summary.
But just talking about the different components in a graph, as well as something maybe just a very high level overview of what CAP theorem is, so we can understand what the problem is.
Right. So basically, any routing protocol, even though we like to make them very fancy and we have all this stuff, and now don't think when I say a routing protocol has simple components that I mean that routing is simple. Tony Lee's going to come on our other show in a little bit, and if he ever hears me say that routing is simple, I'm going to get smacked upside the head the next time I see him. Routing is actually one of the hardest problems algorithmically or in computer science to solve. It's why there's so much research in this area and stuff like this. Cryptography and routing are very difficult. But one of the things that you get into with routing is that there are actually three components to a routing protocol that you need to think about. The first is you have to have a database. You have to have a distributed database that actually allows everyone to see what the topology looks like. So this is more so in a link state protocol than a distance vector. But even though distance vector protocols still have this, it's just not the same thing or quite the same way. The second is, so the distribution of this requires a flooding mechanism, right? So then the second thing you need some way of discovering what the topology actually looks like. I have to have something to put in this database. So that's actually your hello processing. People think of hello processing as more about flooding. It's really not. It's about topology discovery. I need to know who I'm connected to. And that's the primary thing about hello stuff. And then the third thing is an algorithm that actually allows you to compute loop-free paths over that database. There's three basic components there. So when you go back and talk about, there's two things you can overlap in there, and I want to make sure Nick can jump in here any time he wants to, that, just talk over me, Nick, if you want to, is that the two pieces you got to think about are when you start talking about a distributed database, you're actually right in database theory and CAP theorem. So CAP theorem just basically says you can choose two of three. It's consistency, accessibility, and partitioning. So the more you partition a database, the more either you have to give up accessibility. So the easiest way to think about this is if I take a single database and I split it across two machines, I've either got to lock the records during writes so that nobody reads the wrong information out, right? Or I have to reduce the consistency. I have to allow for there to be different results when I read from both machines. That's the basic bottom line of CAP theorem. Now, we treat this quite often in the database world. We treat this like, oh, it's like absolutes. It's 2 out of 3. It's really not. It's really a graded scale. Of the more partitioning you get, either you have to give up more and more accessibility or more consistency. Well, if you think about the way routing protocols work, every router in your network has full access to the entire database constantly. There's no way to lock records in a routing protocol. So what you do is you essentially give up complete consistency in order to get accessibility and total partitioning. So effectively, a routing protocol in a distributed database format is just a totally inconsistent and eventually consistent database. It's eventually consistent, but it's not consistent at any given moment. Perfect illustration, the internet never converges, right? That database is never consistent, never. So that's kind of one piece of it that you get into. Now, when you're building the shortest path, you're using a shortest path first algorithm that treats the network as a graph. So you have edges and you have links, or edges or links or vertices, and then you have nodes, which are your routers. So when we get into talking about how OSPF works quite often, particularly Nick and I will fall into this language of talking about nodes rather than routers, or vertices or edges rather than links. And it's just because that comes out of the graph theorem side of things, and you kind of get into this habit of talking about it that way when you deal with the graph theorem pieces. So
yeah, I'll jump in if I could. Yeah, so just to so I think Russ, what you meant to say is a vertex is a node, right? Like a vertex is a point.
Yes,
not
vertex.
Not an edge.
Sorry.
Okay,
yes.
yeah. This is going. I'm just clarifying. So
I'm reading your show notes, Nick, and I got confused.
I probably typed it wrong.
I'm reading and talking.
Yeah.
I'm reading and talking at the same time. I should never do that.
Yeah,
I should never read and talk. It's a bad thing.
Yeah, don't walk and chew gum. Okay.
That's right.
Yeah. So when we talk about that, let's just take it back up. I know we kind of jumped right in and talked some specific OSPF design over hub spoke, but we'll take a step back and say, at its base, you think about a graph theory in general. And again, I'm not going to be 100% mathematically correct with a lot of this. There are real mathematicians who would reach through the cream stream and strangle me for,
I get
simplifying
slapped all
graph
the time.
theory. But
I get slapped all the time by database people.
Yeah. So
you're misusing CAP.
Yeah. Edges, an edge is a link, and a vertex is a router or a node. Now, the reason that's important is there's some pretty fundamental things in graph theory, and the first is, a vertex has an identifier, and that's really all that is. It has like a router ID, for example, an OSPF, or a name, or a string, or whatever it is. That's, a vertex needs a way to identify itself. An edge, as an object, for those who do object-oriented programming, might have two vertices in it, like as links in a linked list or whatever the structure is, but an edge will connect to exactly two vertices. Okay, that's probably one of the biggest takeaways, exactly two vertices. So within the world of networking, I'll pose the question later, and it might help people to understand a little bit how OSPF works on a multi-access network, but just kind of put that off to the side for now. So an edge connects exactly two vertices. The edges can have things like direction. It could have things like cost as well. And OSPF just happens to be a bidirectional graph in both directions. You can't really, at least I'm not aware, without filtering and knobs, of saying, hey, I have two routers. Each router is going to have its own local cost, which is effectively a link that has costs in both directions, and the graph's always bidirectional. So if R1 has a path to R2, R2 is going to have a path back to R1 if those two routers are connected. Regardless of what the costs are, you can't simply say that R2 can't route back to R1 unless you're going to do something like LSA flooding, in which case you have no consistency in the database.
Right.
So in general, the best way to think about OSPF, it's a weighted bidirectional graph all the time with an edge that connects exactly two vertices. And when you think about the graph that way, and you think about when you're building your network at the most primitive layer, how can you simplify your network and make it more straightforward from a computation perspective? And again, I know Russ had said kind of an old school mentality to think about things like SPF runtimes and OSPF scale within a single flooding domain. And that's generally true, I think, for a lot of networks. But you also want to consider, like in my environment, when you work in like for the U.S. federal government, for example, equipment can be very small, like physically small, which means it doesn't have all the newest technology that might be in an enterprise network or a carrier network or a data center. So those kind of things actually do matter for a little while, as well as very slow links where flooding becomes an issue. So some of those kind of classic OSPF design things actually do matter a lot in some kind of corner case environments, but it's still important, I think, to understand how that works. And from a graph perspective, I guess I'll bring it up now since I'm on the topic, is suppose you have three routers connected on the same LAN segment. How do they form? What's the graph look like? Well, this is actually what, the OSPF network type, for example, will determine. If I had, I just said three routers, let's say it's 100. So suppose I have 100 routers in a LAN segment, they're all running OSPF. If I was running a network type, and if an edge can only connect two routers, that means that from an OSPF neighbor perspective, you'd have a full mesh of OSPF neighbors. Every router would have 99 other ones. And that is possible. Network type point to multi-point, that's what you would get. That's what the graph would actually be. Every router, would have 99 neighbors, 99 links in the graph. This is the idea of the designated router, the pseudo node, blah, blah. It has lots of cool names. When they call it a pseudo node, it's really a vertex in the graph. It's an aggregation vertex. So at a software level, at a protocol level, it's an aggregation node that's invisible. All its costs are zero, but it has a neighbor with everyone on the link, everyone on the segment. So all 100 of those routers would have one neighbor to that designated router that would effectively have 100 links or 100 edges connected to it, and all those costs are zero. So that's, as you think about graphically, what's harder to compute, a giant hub spoke network on a LAN or a full mesh of 100 neighbors? It becomes pretty straightforward algorithmically and computationally, which one is more straightforward to compute. And that can become significant understanding. That, for example, a common recommendation is if you have a point-to-point link, like on Ethernet, and by default, a lot of network vendors will run a broadcast network type, which elects a designated router on a point-to-point link with two routers. Why? You put a node in between for aggregation. Why? You don't need it. So people recommend, that's why you do point-to-point. Speeding up convergence might be one reason, but not having the DR, that's a whole nother vertex in the graph you've eliminated with no trade-off. So things like that, I think, are important to understand from a graph perspective on how designing your OSPF network kind of at a graph theory level can be advantageous.
Right. And trying to understand traffic flow, Nick, I'm backing up 1 second here. The graph is bidirectional, but from any particular router's perspective, it's actually unidirectional.
Yes.
That sounds weird, right?
Yes,
but when I'm computing SPF, I'm actually computing my outbound way to reach everybody on the network. I don't know how they're going to reach me. So therefore, from my perspective, I'm thinking now I'm not thinking about network design perspective. I'm thinking more in terms of, if I'm trying to understand, one of the greatest skills a network engineer can have is being able to look at a network, know the protocol, and know how it's going to converge and how traffic's going to flow without having to look at the routing table. Most of us just go and sit and start typing on the keyboard. They won't let me have access to the console anymore on my network. So I kind of have to do it other ways. So anyway,
they kicked you out. You're not allowed anymore.
No, they offered me access, and I actually don't want the access. So that's another entire problem. But I mean, being able to look at a network diagram and say, where are my flooding domains? And then from that, to be able to understand how, from any router's perspective, the network is going to look and how it converges and where traffic is going to flow. If you think about this graph theory stuff, you can start thinking, well, if I'm sitting at this edge, at this node, I'm going to actually, at this edge of the network in this node, I'm going to build a tree that looks like this, so therefore the traffic I'm going to send is this direction. But then if I'm sitting over here at this node or this vertex, I'm going to actually see a different tree. So now I can start understanding how traffic's going to flow through the network without actually having to look at the routing table. I can actually just see the network and see what's going to happen to it. And when it converges, when a link fails, I can start thinking about, like, how's the traffic going to flow around that failure? And I can start understanding how the network works without actually seeing it happen.
Right.
So
I want to use that as a segue here, because we got really deep there on the theorem, which I think is fantastic. Because I don't seriously, because I don't know how many people have taken the time to dig into that. I think exposure to the idea that there's this whole graph theory about the way that these routers and are choosing their paths, especially when you're talking about Dijkstra and OSPF and ISIS and so on. There's a component in there that we're not actually always considering. But CAP theorem specifically, when we talk about the fact that we have 100% partitionability, right? We have the database on every single router, and we have 100% access because everybody needs access, but we don't have 100% consistency. And this leads into, I think, one of the primary issues with OSPF, and that is microloops and conversions. And so maybe we can talk a little bit about that and how that comes to be.
Yeah. Go ahead, Nick.
I'll talk a little bit about that. So just to describe how does that, I think Jordan summed it up really well, is suppose I have a big ring, say 7 nodes. Odd numbers make this a little bit easier. So I have 7 nodes in this ring. One of the node links break, let's say between the 3rd and the 4th router. That, when that happens, I have this big ring. All the nodes are going to, assuming single area, there's going to be a flooding event. The nodes are going to individually run SPF to find the shortest path. So when R3 tries to reach R4, it used to be a direct link. Now it's going around the whole ring. But when R3 goes to do that, let's say his next hop is supposed to become R2. R3 might be sending packets to R2 before R2 realized that his shortest path isn't through R3 anymore. And again, you can kind of think of it. He doesn't know yet. So it'd be like me coming to you. It's almost like being at work and saying, hey, I got asked to do this new project, or the meeting got moved till 1 o'clock. Did you hear yet? No, I didn't. And then 2 seconds later, that guy's phone buzzes and he gets the text message. And he's like, oh, now I know. So things like that is kind of a human way to help describe that. But in that particular issue, you get traffic that loops back and forth between R2 and R3. And in the Edge or P-Show, we talked a little bit, is it a big deal, yes or no? And I'll offer it depends. And the reason here's some kind of real life examples is if you're in a data center environment, and again, you wouldn't see rings in a data center too often, but just bear with me. If you're in a data center environment, you have a Microloop, and it's a 100 gig link or something like that, and the devices have generally shallow buffers, and it doesn't take a long time for a device's buffers to fill when there's 100 gigabits per second of traffic over it. Microloops can be fatal. But if you're in an environment where maybe the traffic flow is less, maybe you're in some kind of really heavy voice, a VoIP type environment where most of the flows are benign, and it would be better to loop the traffic for a fraction of 10 milliseconds or so. Better to do that and take the latency, assuming the TTL doesn't expire, of course, and forward that traffic on than to have it be completely dropped. That might be okay. Now, if you don't want microloops ever, again, EdgeRP and BGP can both do that. OSPF and IS to IS are going to have to think through that process a little bit, and you would do that either using something called ordered fib, which I think Russ is probably more qualified to talk about how ordered fib works, but I'll talk for about 1 minute about how loop-free alternative paths or LFAs work. Effectively, what LFA does, and in a ring, you need kind of a special, remote LFA, you need to do some encapsulation, things like that, but without getting into the mechanics of how LFAs work, the general idea is if you run SPF from your neighbor's perspective in advanced, you can not in rings, but in a general network. If you run OSPF, you look at all your neighbors, run OSPF from their perspective, because again, assuming eventual consistency, you're going to have what their database is. You're going to know their paths in the network, and you can run SPF from their perspective, effectively finding out what is their path going to be to get to this destination, and can I use them as a next hop in the event one of my links fail? And that's at a high level how the LFA process works. And with remote LFAs, in a ring, for example, from R3's perspective, his only other neighbor is R2 in a two-connected network, or a ring is a fancy way to say a ring. Send traffic to R2, he's going to loop it right back. But it would be better if I could tunnel that traffic and maybe up to like R1 or somewhere past R2 to a router that wouldn't loop it back. And today, that's generally accounted for. At least one of the first methods was using MPLS encapsulation with LDP. Effectively, tunnel the traffic somewhere traffic exits the tunnel and gets routed normally back down to the destination. So you're still going the long way around the loop. You're just tunneling halfway to a node in the center. And we could, the math behind this is actually quite difficult. It's known as the PQ node. It's effectively the intersection of two different spaces. Again, not really a podcast level.
It's going to be incredibly difficult to explain here.
Yeah,
so we're not going to dive into it now.
The general idea is not too bad.
The easiest way to understand it. The easiest way to understand it for somebody who's familiar with distance vector is it's essentially around the same place or the similar place, and most of the time it is the same place as where you would do split horizon. So if you think through the ring and you think where split horizon happens, that's your PQ split. And if you can tunnel past the split horizon, then you're fine. That's essentially what it comes down to.
Right. If you think of the ring as circular, on the opposite end of the ring, that router is going to be
a square ring.
Yeah, you get the idea. I'm saying if you think about it as circular, the router that's on the other side of the ring is going to have to make a decision. Do I go the top path or the bottom path? Right. And it's the first router who decides to go the other way.
Right. That's
the
right.
other way
exactly
is the faster way. Right. I mean that's.
Yeah,
and that's the point. So if you were doing, remote LFA, you would tunnel to that node because that node is already making the opposite decision, has already converged on the direction you want to go.
Right.
That's pretty
wouldn't
deep.
Another way to think about that be that the router whose flow to that destination would not change when that link dropped? Right. So
yes.
When you have the
absolutely,
event, right?
Yep, that's exactly right.
Yeah.
Yep.
Now to discover that takes a little bit of work. I mean, I think I can describe it in about 20 seconds, so I'm going to attempt it. But
we're timing
process,
you. No, I'm kidding.
So the P space is the set of routers from which the router sending traffic. So in this case, I think it was R3. What are all the routers that I can reach without going over the failed link? So just pretend the link was up. Right. What are all the routers that I can reach? And that might be the left side of the circle. Like I can hit all these guys without taking the counterclockwise approach. So that's my P space. The Q space is the set of nodes that can reach the destination without going through that failed link. So basically, I want to find out how can I get to that node at the top? And then I want to say, what are all the other nodes that can reach the destination going the other way? And ideally, there's going to be a point where those two things intersect. And in a ring with an odd number of nodes, like 5 or more, it will always be exactly one node, and that'll be the PQ node.
Yep. That's why odd nodes are easier to compute. Now, before we jump too much further into LFA and stuff like that, there's one point I want to bring up that actually one of the reasons that people find OSPF difficult to deal with when I was in TAC and escalation is that they get mixed up in their heads about IP addresses and IDs.
Yeah.
Right? I don't know how many times I've done a show IP OSPF database all, and somebody looks at it and goes, well, that IP address should be reachable because, hey, that's showing up here. I'm like, that's a type 1. That's a router LSA. That's not a reachable destination. That is a router ID. That does not mean the destination is reachable. What do you mean? It's an IP address. No, it's not an IP address. It's a router
looks
ID.
like one.
It's a string.
It just
plays
looks
one on
like
TV.
one.
It's a string.
It just plays one on T1. That's right. So all link state protocols work the same way. You discover your neighbors. You build your graph based on your neighbors. You have nothing to do with IP in building your graph. Nothing at all. IP has nothing to do with neighbor discovery or anything like that, except you carry the packets over IP, blah, blah, blah. But within the actual process of discovering neighbors and building your SPF tree, there's nothing to do with IP in any of that. It's just router IDs. And then once you've built that, then you actually hang your IP reachability off of the graph. So if you actually think of it like a tree, and those IP addresses, so the branches and the root and everything else are all the actual nodes, and then the actual leaves are little IP addresses that are reachable. That's actually what's going on. They're actually called leaves for that reason. So I just think it's a big thing for people when they look at the OSPF database, they start thinking mentally, they think that that's an IP address. It looks like one, like Yvonne said, it plays one on TV, but it's not. Stop thinking about it as an IP address, and it'll make your life working on OSPF a lot simpler.
Right. I mean, when you run like v3 and you're running IPv6 segments across it, right? You're still using that 4-octet address as a router ID, and so all it is that identifier. I mean, my assumption, right, is, and I don't know if this is necessarily true, right, that but it seems like it was picked because then it could use IP addresses as the ID. You could just fall back and identify itself as an IP that was on the box, but that doesn't necessarily mean. I mean, you can assign whatever ID you want. The ID on the router can be 1.1.1.1, and there doesn't have to be any address on the box that's 1.1.1.1, and it has nothing at all to do with the reachability to 1.1.1.1, right? It's just simply an identifier. Yeah.
In fact, some of the most confusing networks I've ever worked on are OSPF people who go out and put router IDs in that are actually reachable IP address in their network, but it's not reachable from the router that they've used the ID.
But it's not associated with the router it's assigned to, right?
Yes.
Yeah.
Oh, that's horrible.
It's like naming all your kids Joe, right? I mean, you
Exactly.
it's like, I don't know which one it is, right?
Yeah, it's horrible. The other horrible one I ran into once was somebody actually numbered all their OSPF areas Area 51, even though they weren't all the same area.
Yeah, that's fine.
Yeah, that's a little difficult. Although I think I could defend that in some environments. And hear me out, because imagine again within the place I work.
It was you, Nick, wasn't it?
No, I did it. I did it. Except that I did actually.
He does work military, so
I did do it. It wasn't Area 51. It was Area 1. But anyway, what the logic was, we had a big kind of. Unfortunately, it was a hub spoke network. We couldn't really make it work the nice way that I liked. But anyway, we had this big kind of OSPF Area 0. But the remote stations that show up when they need to. They're trucks. Sometimes they're parked. Sometimes they're doing a mission. Sometimes they're not. It would be really, and there's thousands of these things. It would be really convenient if they all had the same configuration in their baseline. The only thing that has to change is the IP addressing. So what we generally do, instead of tracking OSPF areas for every single truck that this particular organization was using, it would be a lot more convenient just to put them all in Area 1 and just have different separate Area 1s everywhere, because they never connected laterally. They never needed to. So
right, because the only issue would be communication between devices within Area 1 wouldn't work that way.
Actually, it doesn't matter. It doesn't
matter.
At all.
It will. No. So in Area 1 will traverse to Area 0?
Yeah, so area 1 to 0 to 1 absolutely works. It's not like the area ID itself isn't really relevant outside of that little bubble. So so in our case, we could get full reachability that way without the additional burden and the operational expense that it would actually cost us, I don't know, I wouldn't say millions, but it would cost the government a lot of money just to track all the numbers for all these different assemblages through the Army when we could just do Area 1. Because it's a new piece of information that we suddenly need to start tracking, because initially we had a flat Area 0, had issues. We'll go through some kind of classic OSPF refactoring, and we ended up with something like that. But then we're like, oh, do we want to have a different thing for a truck? And I said, no, we don't technically need that. And I'm not sure that's going to add any business value. So that was one. Now, if you had a more static network, I might say, yeah, do it, because you're not going to have 5,000 Area 51s or 5,000 Area 1s. You probably have, however many. It wouldn't be a number like we saw, but in that particular case, it kind of made sense to have a more consistent deployment model so that the configuration baselines were kind of the same.
So the moral of the story here that I'm hearing is that Nick missed out on an opportunity, because that could have been Area 51. It would have been a completely valid design, and it was just a complete missed opportunity.
I could have done that. We're not very creative. We're like, 0, let's just count. We'll do 1.
We'll just next one. Well, that makes sense. Sounds like an engineer.
Yeah, there you go.
Russ, you talked about, since we're on the topic of databases and areas, I think Russ and I want to talk a little bit about the purpose of a Type 4 LSA and what it does. And I think that
why a Type 4? You have all of the types, and you want to talk about Type 4.
I think Type 4 is really poorly understood, and its use isn't really well understood. And I know Russ has some really good tie-ins for how it ties into some of the complexity theory that he's developed and authored books on. So I'll let him talk about that aspect, but I at least want to summarize the technology and why it's useful. So the idea of the Type 4 LSA, I can summarize it in about 10 words, and it's when you're performing an inter-area lookup on an external route. Okay, so the logic of this, again, you have 3 kind of bubbles. You have, we'll say area 1, area 0, and EIGRP. Okay, so you got 3 separate bubbles. There's a router in area 0 doing redistribution from EIGRP and OSPF. So now within area 0, I've got these external routes, Type 5s, we'll say. I've got external OSPF routes inside this area 0. All the routers in that flooding domain. So within that graph, those guys all say the ASBR's router ID is 10.0.0.1. I have a router LSA for it. I know my shortest path to it, and I'm able to reach those external destinations. Because the interesting thing about external routes, at least true for Type 5 external LSAs, is that the originator ID doesn't change. As that thing gets flooded through the whole OSPF domain, notwithstanding stub areas, we'll ignore those for now. The originator never changes. So that 10.0.0.1, that ASPR that did the redistribution, that router ID, that node in the graph, that vertex identifier never changes. So in area 0, everyone knows about 10.0.0.1 because they're all sharing area. They have a router LSA for it, no problem. But what happens when the ABR between area 0 and 1 on the other side of the network floods that external LSA into area 1? Those guys go to say, oh yeah, let me look at my router LSAs. Oh, I never heard of that. Why hasn't he heard of it? Well, because the Type 1 flooding boundary is at the ABR. We don't share that level of graphical information between areas. We effectively have more of a distance vector model where we have a summary LSA. Again, I'm not trying to talk too much about LSA types, but the Type 3 basically says I'm going to take all the basically the routing information. I'm going to summarize that, not summarized by routing, but summarized by topology, and say I'm going to give you the cost to reach it, and I'm going to advertise it for myself as being the router that is originating that summary LSA. So you can reach this destination through me, very distance vector based. For the the purpose of Type 4 becomes interesting because the ABR is the one who originates that. And he originates it, floods it into area 1 in this case, so that the routers in area 1 can, again, do that inter-area lookup on the external route. Because in order for routers in area 1 to reach the external routes with the EIGRP, they need to know how to do a lookup, in the graph to reach 10.0.0.1. That's what the Type 4 does. So for those who don't, may have struggled with that concept, and I've heard some people summarize it as the next hop information. I personally don't like that. I felt like it was too vague. Inter-area lookup on external routes is my personal best way to remember that. So Russ, do you want to talk a little bit how that plays into SOS?
Yeah. So it's interesting actually that you say it, that you get into this whole thing with Type 4s because, well, first of all, I'll tell you that we're now giving away one of my favorite interview questions ever.
Oh, listen up.
What do we win? What do we win?
So if you ever interview with me, one of my favorite questions is what is a Type 4 used for? Because so few people know it, and it's so crucial to the basic operation of OSPF and understanding externals and internals. But as Nick said, first of all, you have to think that you have a Virtus, right? So you actually have this node that has an ID. And the ID is going to be taken out by this summary. Well, there's another thing that's interesting about this, which is that when you go through that summarization point and you remove that topology, imagine that I have area 1. Since we're using Nick's area 1, we won't use 51. We'll use area 1 just to make Nick happy. I wouldn't want to strain you, Nick, and make you go to area 2 or anything. But anyway, when I go from area 1 to area 0, I may have 5 different entrance points into area 1. And if all I know going between those two is a next hop per se, then I don't know from area 0 which way to get into area 1 is the best way to get to that external route. In fact, it may turn out that one of those ABRs that's on the area 1, area 0 boundary could actually be doing the redistribution. And I just don't know because all that information has been summarized out. I don't know anything about the topology in area 1 from area 0's perspective. So what I'm going to do here is I'm going to inject this type 4, which actually is injected by the ABR. And that's another thing that's weird about the type 4 is that it's actually injected by the area border router at the flooding domain boundary. And the reason that's done is because, first of all, the ABR is the one doing the summarization. It knows that information is going to be missing. But beyond that, it knows that it has, one of those ABRs has the best path to reach that ASBR, that autonomous system border router. And it's going to be the one who builds the type 4. So that way you know where the best way to enter area 1 is in order to get to the shortest path to that external border. So that actually gives you the information back. So this relates back to SOS because I have state, optimization, and surface. In this case, I'm reducing my state by summarizing the topology information, but I'm actually losing my optimization, not only in not being able to reach it, but I'm not even able to reach it properly. I don't know the best path to get there. The type 4 actually re-injects the optimization by, guess what, re-adding the state. So I'm actually re-adding state to get back in.
So the risk here, if the type 4 didn't exist or the information was incorrect, right, is that either I wouldn't know how to get from area 1 to area 0, or if it came from a router that wasn't the best possible path on the shortest path tree, I could end up, if there were multiple routers, I could end up sending my traffic to the wrong ABR, which then would take a suboptimal path to get there.
Yeah, okay. If you had a knob to disable it, and I'm not really aware of one other than getting creative with stub areas, but assuming you had a knob to turn it off, originating a default or doing some kind of prefix aggregation on an ABR could technically solve it, but it goes to Russ's point, is that may not be the optimal exit path from that area to reach the external destination.
And that's true of stub areas, right? Anytime you do a stubby area or a totally stubby area or whatever, and by the way, the easiest way to remember this is that stubs, let me get this right in my head before I say this. I don't do a lot with OSPF, so a stub area essentially blocks anything but any of your internals. A totally actually blocks your externals as well. So a not sto gives you the externals back, but through translation mechanism. Did I say that right, Nick? Did I backwards?
Well, yeah. So so the totally basically says your internal routes that would come in as summary LSAs.
Right. Yeah, I said it backwards.
Summarized into a default. The stub area will allow those to come in, so you get more state with the regular stub, less state with the totally. Generally, you can, and they don't have to match. I mean, there's no bit in the OSPF that says all your ABRs have to agree on whether it's totally or not. So what you could get creative, if you had multiple ABRs, for example, you could say, I want one ABR to be backup only. He's going to be totally stubby, so he only injects a default. The other guy is going to be my primary ABR, injects all the longer matches. So you can get kind of creative with that. So
stubs block externals. Yeah, stubs block externals, totally blocks internals. And then not so re-injects the externals on a selective basis by using this silly translation stuff that goes on.
Yeah, outbound only. So you can do redistribution inside of an NSSA and routes go out, but under no circumstances in any kind of stub area
does an external still come back in. Exactly. Right. So you're still using your default. Yep. So that's actually kind of important for people who are designing OSPF. I personally don't use stubs and totalies anymore. I use type 3 filtering because it's so much cleaner and so much easier to design and so much easier to understand exactly what's going on when I do a type 3 filter. I know exactly what's being allowed in and what's not being allowed in to a particular area.
The biggest trade-off there is that you can't do anything with external routes. You're stuck with them.
Right, you can't do anything with external routes.
So if you don't have, that's a good point. If you don't have a lot of externals or you don't care, you just want them to pass through, then Russ's strategy is probably the best one. But if you need some way to control external routes across those ABRs, you're basically stuck with a stub area. And you just kind of have to think through how to engineer your network around that.
Yeah, that's exactly right. Yeah.
All right, so we've talked through a lot of deep dive details about OSPF. What do we think about the future of the protocol? What's next for OSPF?
Well, I'll offer something kind of high level, and I know Russ has much more involvement with the IETF standards bodies and R&D than I do, but I'll offer kind of two things quickly. One, I feel like some of the future things in OSPF are almost trying to make it look like IS to IS. Russ has probably talked a little bit about some of the TLV type work that's going on with OSPF. But one thing I thought was interesting was kind of a common case in OSPF where a link can only be inside of one OSPF area, or that was traditionally the case. And RFC 5185 came out a few years back, and the only reason I'm citing it is so that people can kind of Google it and learn about it, but it's called multi-area OSPF. And that name's really not, well, of course, OSPF is multi-area. This is talking about on a single link. And the reason that can be valuable is if you have two ABRs and they're connected together with a link, and you have OSPF, 0 on top and 1 on the bottom, what area should that middle link be in? And traditionally, you had to make a choice based on 0 or 1, and there were trade-offs depending on what the topology looked like on either side of it. So now, even though you're trying to determine what area should this cross-link be in, you have to basically look at the whole network on either side of it to make that call. And IS to IS inherently never had this problem because the flooding domains in IS to IS are like ships in the night, for lack of a better term. You could put it in both IS to IS levels and not have the problem at all. So the nice thing about IS to IS, it inherently solved this problem with its protocol design. OSPF was kind of playing catch up years later and said, it'd be really cool if on just a basic point-to-point link between two nodes, we could run it in multiple overlapping areas so that we can have, from an area 0 and an area 1 perspective, for example, have the best path between those nodes. And that becomes relevant because, as you know, in OSPF, you always have to prefer the intra-area over the inter-area. So if you get traffic to a router that only has inter-area routes, or maybe has a really bad intra-area path that kind of figure eights through the whole network to go out versus a really good inter-area path up to the backbone, you can't use it. You have to take the really bad path. And this particular feature helps you get around that in the same way IS to IS does, except using kind of a bolt-on OSPF feature. So I know that's not like future, but it's relatively new, and I thought that people should know about that for their designs.
Yeah,
I found it useful on the campus.
Is this implemented widely, Nick? Do you know? I don't even know.
I don't know that it's implemented widely. I know for sure that the newer Cisco iOS releases support it for sure, as I've done it there.
Okay.
I can't speak too widely to it, but it definitely is a standard, and it does work. And it's kind of an interesting thing, and I just looked at it when I first learned about it. I was like, this sounds familiar. It was definitely borrowed kind of a concept from IS to IS.
Yeah. Well, basically, in IS to IS, you have two different neighbor adjacencies anyway, one at level 2 and one at level 1. In OSPF has always been designed to have one single neighbor adjacency on every link. So the whole process of doing 5185 essentially involved building a way to build a second neighbor adjacency on OSPF in a way that the sockets and the protocols would actually make it work well. Yeah. So, and you mentioned TLVs. A lot of work right now is going on into TLVs and using TLVs in OSPF v3. So all of the LSA types are being replicated in a TLV format to get it closer to an ISIS perspective. And you might say, well, why didn't OSPF just use TLVs in the first place? That's kind of crazy, right? But the reality is when OSPF and ISIS first came out many, many years ago, processors were much smaller. I mean, we use this excuse all the time, but it's true. Processors were much smaller. I mean, we're using 8-bit and 16-bit processors were a big deal back then when they first came out. Cisco boxes were running RISC processors at that time, and all 8-bit, and like I said, there was some 16-bit. That was a huge deal. And not having to sort TLVs, not having to actually tear a packet apart, TLV, but having everything fixed length made a huge difference in the performance. So OSPF went with fixed length fields. Now today that doesn't matter so much. So there's a lot of work going into OSPF v3 to make it TLV based. Another interesting thing that's going on, I've heard about this, but I haven't seen any drafts on it. By the way, the TLV based drafts, you can actually go with, you can actually go out to the IETF and take a look at it and watch those drafts and actually participate. You can actually read them and make comments if you want to. So that's something new that's going on right now that you could actually get involved with if you want to. It's pretty interesting.
Very good. Well, Russ and Nick, thanks a lot for joining us. I know that this is...
But wait, we have more to say.
Okay.
There's always more to say on the topic, but maybe later.
Sorry, Yvonne, I just had to do that.
It's fine. It's fine.
What your mama didn't tell you about OSPF, episode 2.
Right. That's right. Part 2. All right. Jordan, why don't you tell us where we can find you online?
Sure. You can find me at my website, jordanmartin.net, or on Twitter at bcjordo.
All right, and I'm Yvonne Sharp. You can find me on the blog at esharp.net or on Twitter at Sharp Network. Thank you for joining us for What Your Mama Didn't Tell You About OSPF.